Everyone, welcome to another fantastic math video that I know you're looking forward to. This video is going to be on the normal distribution curve, which you probably don't know what it is, which is why you're watching this video. So let's get started. First of all, this is something that's actually used a lot in life, in different jobs, and it's actually kind of useful to understand and know what's going on. So first of all, we're going to talk about what it looks like, then I'm going to describe the parts and kind of why it's useful. So first of all, normal distribution curve, the curve is going to look something like this. There's this kind of big long line, but the curve itself is going to go like up and then curve down like that. And because I don't like things to be uneven, I'm going to put that there too. This is a normal distribution curve. It is supposed to be symmetric on both sides, but I am kind of eyeballing it. Just know that this is supposed to be exactly the same on the left and right, split right down the middle. And this right here, this long line is a number line that I'm going to be using, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It's not necessarily those numbers I just said, but it is a number line. And the parts of a normal distribution curve is right in the middle is going to be the mean, which, if you've forgotten, mean is just the math word for average. So if you have a bunch of data, the average is the mean, and that's going to be this number right here. And then since this is a number line, it's going to go up over here and it's going to go down over there. But what do you label it by? Sometimes you go by ones, sometimes you go by sevens, sometimes you go by 5,000s, sometimes you go by 0.038. We don't know what the scale is going to be. Well, you kind of do actually. The scale is going to be something called the standard deviation, which I'll write down. Standard deviation. That's the scale you're going to be using on this number line down here. So just as an example that I'm completely 100% making up, let's just pretend we were talking about heights. We wanted to talk about how tall some people were, and they were taking a big survey to finding out the heights of a bunch of people in, I don't know, let's say a high school. And they found that the average height of people was approximately 5'7". So that would be the average right in the middle. And then they did a bunch of math stuff, and they found out that the standard deviation was 2 inches. Just because you'll eventually see the symbols, I'll write them down here as well. Mean, the symbol people use for mean is mu, which looks like that. Standard deviation, they use this little thing, circle with a hat on it. So when you see those symbols, that's what it means. Anyway, so the standard deviation is 2 inches. That means we're going to go forward 1, 2, 3 times an equal amount in both directions. 1, 2, 3. I'll talk about why in a second, but if you go forward 3, this would be 5'9". This would be 5'11", and this would be, let's see, 12 inches is 6 foot, so this would be 6'1". This would be 5'5", 5'3", and 5'1". Oops, that's supposed to be 1, 2. There we go. So you go forward that many. Always 3 in both directions. And now it's time to throw some numbers in there that, once again, I'm going to describe afterwards. In a normal distribution curve, these are going to be percents under here. This section is going to be 34% of the data. This will be 13.5% of the data. This will be 2.35 and then 0.15% of the data. And like I said, it's symmetric, so these same numbers will be over here, 0.15%, 2.35%, 13.5%, and 34%. This, by the way, is called the empirical rule. Empirical rule. The empirical rule. the reason these percentages are what they are is somewhat because they just wanted to define it that way. Other parts is because they want things to be easy. For instance, one standard deviation we said was 2 inches. So one standard deviation this way and one standard deviation that way. The phrase they use for that is within one standard deviation. Within one standard deviation, or within 2 standard deviations, or within 3 standard deviations. And what happens is 68% of your data will be here, in this case height. That means out of everyone surveyed, 68% were between 5'5" and 5'9". If you go out another standard deviation, you can either check or you can trust me that this is 95% of the data, showing that 95% of people were between 5'3" and 5'11", which, this is not exact. I made these up to make the math easy, but it should be like not surprising if I was to tell you it was actually true, because most people are taller than 5'3" or below 5'11". And then when you go out the last one, that would be 99.7% of people are taller than 5'1" but less than 6'1". That's not going to be true. If you go to a high school, there's people taller than 6'1". But in the people surveyed or whatever, you would see that pretty much everyone was between 5 foot and 6 foot. There would be some outliers who are above or below that all the time. That it's going to happen, but it's only 0.15%, which is very, very small. And that's what's going on here. That's why this is useful. They call it normal distribution. I like to think about it, it's because it helps define what normal is. It's normal to be within this range. Most of the time when scientists or doctors or anyone who is doing anything with numbers, when they're trying to see what is normal and what is not normal, they use a normal distribution curve. Especially I had kids. I have 2 kids. So doctors would often talk about me. It's like, oh yes, your kid is on track. Your kid is within normal weight. They have average height. When you go in for your 1-year checkup, it's just you want to know if they're normal. And this is what they would do. They would say, well, they're within 2 standard deviations. So they're on track with 95% of the population to being healthy and normal. It's only if you're outside that, then it's like, well, you're in the weird 2.5% or 2.5% where you're either too much or too little of whatever you're talking about. So this is something that is used a lot, and it's very useful. Of course, we're going to do a very much less useful example here to go on. In this one, it's just talking about potato chips, not exactly healthiness of children, but it is something that is used in businesses as well. And here it says, a machine fills 12-ounce potato chip bags and it places chips in bags. But not all bags weigh exactly 12 ounces, which, if you think about it, you probably already knew this. I don't know if you do this, but whenever I go shopping and I'm buying some chips, I kind of squeeze the bags a bit and see which one feels like it has more in it, because they're not all the same. They're advertised as the same. If you look at the front label, it says how many ounces it is. But the thing is, it's not exactly that amount of ounces. It could be a little bit more. It could be a little bit less. Who knows? No one. But you can find out the probability that it is more or less or exactly that. And this is how. It says the weight of the chips is normally distributed with 2.4 ounces with a standard deviation of 0.2 ounces. So they would just, make a whole bunch of chips. Then they would weigh what they actually were after the machine made them. So to do that, I'm just going to use a straight edge this time. Sketch a normal distribution curve. I'll go up, I'll go down, something like that. Doesn't need to be perfect. This is the average, which they said was 12.4. And then 1, 2, 3, 1, 2, 3. And then it's the average. This is the standard deviation. So 0.2 is what you're counting by. It's the scale. So I'll go up by 0.2s and I'll go down by 0.2s. So this would be 12.6, 12.8, and 13. This would be 12.2, 12.0 or just 12, and then 11.8. So the scale is 0.2 because that's the standard deviation, right? That's the scale. The percentages never, ever, ever change. Ever, ever? Or never, never. 2.35, 0.05, 34, 13.5, 2.35. So just every single time you have to do a problem, just make one of these. It's easier than trying to do things in math or on a calculator. Just write this out, and it turns out a lot simpler. Just write one of these things. The black part always stays the same, right? Those stay the same. Never, ever change the numbers. They are just definition of normal distribution. It's only the stuff in red that can change. The scale and the average can change. But that's it. We're just going to use this figure to answer everything else. And once this is done, it actually does go kind of fast. It says, if you purchase a bag filled by dispenser, what is the likelihood that it's less than 12 ounces? Well, you just go, well, 12 is right here, right? How much is less than 12? It's going to be that 0.15 plus the 2.35, which is exactly 2.5. And that's going to be a percent. So it's just you add up the part here. Less than 12, right? This is 12, then less than 12 is this part. And you just add up those numbers. For the next one, because yes, we're done. If you purchase a bag, the dispensers, what is the likelihood that it is more than 12? Well, you go here, if this is 12, you want more than 12. So you would add these numbers up. 13.5 plus 34, etc. I'm going to cheat because this is half of the data. And if this is half the data, that's 50% of the data. So I'm just going to go ahead and start with the number 50 there. So this is 50, and then plus 34 plus 13.5. Plus 13.5. So yeah, 13.5 plus 34 plus the 50 over here, which is going to be, let's go, 84 plus 13.5. That's 7. So 97.5 it looks like. Okay. Sorry, excuse me. Yeah. That's it, percent. So what's the likelihood? There's a 97.5% chance that it's over 12 ounces. Keep in mind, that's what companies want. Just kind of go back to what the question was saying. It is advertised as 12 ounces. It's advertised as 12 ounces, and it's going to be that or more, 97.5%. And this is very common in companies. You never want to like advertise what the average is, because then, your customers can come back and say, hey, you gave me less than the advertised amount half of the time. And you don't want that to be the case. You don't want literally 50% of the time it's false advertising. It's impossible, really, with standard deviation stuff. I'm not going to say impossible. It's very, very, you're never going to get this 100%. It's just implausible to kind of do that because, if you want to go with 90%, you're going to have to start advertising things like 11.6. And you don't want to advertise 11.6 because that's less than 12. People like looking at the number 12. So they want this, a good space where it's an even number, people like looking at it, and at the same time, almost everything is going to be that or more, because people won't complain about more. This is only like 2.5% of the time they're off, and that's like understandable kind of error, so people won't care as much. So I have two more examples using the same figure, of course. If a convenience store bought 300 bags, so this time we have an actual amount. How many would have less than 12.6? So the first thing you want to do is find percent, right? In the previous ones, that was just it, find the percent. But the second step is once you find the percent, you have to find amount that it would be. Because, if there's 300 bags and it's like 20% or whatever, you'd have to find 20% of 300 to find the actual answer. So let's go ahead and do that. It says, how many would have less than 12.6. So I'll go to 12.6, which is right here. And you would add up these numbers. Once again, this is 50 because it's half of the data. 50 plus 34 is 84%. So it's 84%. So you have to find 84% of 300. So if you don't know how to do that, 84% is the same thing as 0.84 as a decimal, and you just multiply that by 300. So 252. So 252 bags will have less than 2.6 ounces. Why is that useful? I don't know. So in the next one, if a convenience store bought 200 bags filled with dispenser, how many would have between 12 and 12.6? So this time it's between... Sorry, I already forgot the numbers. 12 and 12.6. So here's 12. Here's 12.6. It's saying to add up the numbers between 12 and 12.6. So that's 34, 34, and 13.5. So 34, 34, 13.5. 34, 34, plus 13.5, which is 68 plus 13.5, which is going to be, let's see, 3 plus 8 is 11, 81%. Let's double check because Mr. Anderson's paranoid. Sweet. Okay, so that is the percent. But once again, you have to take that and multiply it by the 200. So 0.815 times 200 is 163. Which is good. That's good, right? 12 to 12.6. So that is, it's the advertised amount or quite a bunch more, you know. 163 out of 200, that's a lot. So most of them are going to be the amount you want or a bit more. And there you go. That's how you do it. Once again, those first two questions were just finding the percent if it asks for a percent. But then if it's giving you a total, you have to find the percent and then also multiply. So make sure you are changing it to decimal when you multiply. So decimal would be 0.84. And then you multiply it by 300. Or in this one, when it was 81.5, you have to change it to 0.815 and then multiply it by the total. But it does have to be the decimal. Okay, that's it. I'm sure you guys are getting sick of my voice, so I'm going to go ahead and end it there. Thanks for joining me. Bye.